Additional notes on sprites. Now that you've experimented with sprites, a few more words are in order. First, you can change a sprite's color to any of the standard 16 color codes, 0 to 15, that were used to change character color. These can be found in Chapter 5 or in Appendix G. G, for example, to change sprite 1 to light green, type poke V plus 40, 13, be sure to set V equals 53248. You may have noticed in using the example sprite programs that the object never moved to the right-hand edge of the screen. This was because the screen is 320 dots wide, and the X direction register can only hold a value up to 255. How then can you get an object to move across the entire screen? There is a location on the memory map that has not been mentioned yet. Location 16 of the map controls something called the most significant bit, MSB, of the sprite's X direction location. In effect, this allows you to move the sprite to a horizontal spot between 256 and 320. The MSB of X register works like this. After the sprite has been moved to X location 255, place a value into memory location 16 representing the sprite you want to move. For example, to get 2 to move to horizontal locations 256 to 320, poke the value for sprite 2, which is 4, into memory location 16. Poke V plus 16, 4. Now start from 0 again in the usual X direction register for sprite 2, which is in location 4 of the map. Since you are only moving another 64 spaces, X locations would only range between 0 and 63 this time. This whole concept is best illustrated with a version of the original Sprite 1 program. Line 60 sets the most significant bit for Sprite 2. Line 70 starts moving the standard X direction location, moving Sprite 2 the rest of the way across the screen. Line 100 is important because it turns off the MSB, so that the sprite can start moving from the left edge of the screen again. To define multiple sprites, you may need additional blocks for the sprite data. You can use some of BASIC's RAM by moving BASIC. Before typing or loading your program, type poke 44, 16, poke 16 asterisk 256, 0, new. Now, you can use blocks 32 through 41, locations 2048 through 4095, to store sprite data. Binary arithmetic. It is beyond the scope of this introductory manual to go into details of how the computer handles numbers. We will, however, provide you with a good base for understanding the process and get you started on sophisticated animation. But before you get too involved, we have to define a few terms. Bit. This is the smallest amount of information a computer can store. Think of a bit as a switch that is either on or off. When a bit is on, it has a value of 1, when a bit is off, it has a value of 0. After bit, the next level is byte. Byte. This is defined as a series of bits. Since a byte is made up of 8 bits, you can actually have a total of 256 different combinations of bits. In other words, you can have all bits off, so your byte will look like this. And its value will be 0. All bits on is, which is 128 plus 64 plus 32 plus 16 plus 8 plus 2 plus 1 is equal to 255. The next step up is called a register. Register defined as a block of bytes strung together. But in this case, each register is really only 1 byte long. A series of registers makes up a register map. Register maps are charts like the one you looked at to make your balloon sprite. Each register controls a different function, like turning on the sprite is really called the enable register. Making the sprite longer is the expand X register, while making the sprite wider is the expand Y register. Keep in mind that a register is a byte that performs a specific task. Now let's move on to the rest of binary arithmetic. Binary to decimal conversion. Using combinations of all 8 bits, you can obtain any decimal value. from 0 to 255. Do you start to see why when we poked character or color values into memory locations the values had to be in the 0 to 255 range? Each memory location can hold a byte of information. Any possible combination of 8 zeros and L's will convert to a unique decimal value between 0 to 255. If all places contain a 1, then the value of the byte equals 255. All zeros equal a byte value of 0, 0 0 0 0 0 0 1 1 equals 3, and so on. This will be the basis for creating data that represents sprites and manipulating them. As just one example, if this byte grouping represented part of a sprite, 0 is a space, 1 is a colored area. Then we would poke 255 into the appropriate memory location to represent that part of the object. T1PF. To save you the trouble of converting binary numbers into decimal values, we'll need to do that a lot. The following program will do the work for you. It's a good idea to enter and save the program for future use. This program takes your binary number, which was entered as a string, and looks at each character of the string, from left to right, the mid $function. The variable C indicates what character to work on as the program goes through the loop. The SAL function, in line 30, returns the actual value of the character. Since we are dealing with numeric characters, the value is the same as the character. For example, if the first character of AS is 1, then the value would also be 1. The final part of line 30 multiplies the value of the current character by the proper power of 2. Since the first value is in the 2t7 place, in the example, TL would first equal 1 times 128 or 128. If the bit is 0, then the value for that place would also be 0. This process is repeated for all 8 characters as TL keeps track of the running total decimal value of the binary number.